So we have slowly been thinking about areas under curves. We started with lower and upper areas. Then Riemann came along and said it wouldn't matter what point you chose in the middle, it would still give you the same area if you did tons of rectangles. So that let us get it a little bit easier because we could just worry about the left side or just the right side or just the midpoint. And then we were like, oh, maybe trapezoids would be even better. So we're slowly making this better and better. And what we're leading to is the definite integral. So again, here's an idea. We've got some sort of sine curve that's been shifted up. And you want to find the area under the curve with a bunch of rectangles. If you look at one of those tiny rectangles, right? Here would be our lower rectangle, and here would be our upper rectangle, and there's the curve in between. Obviously, the upper rectangle is too much, the lower rectangle isn't enough. Notation-wise, what we're going to do is this is our y value. This is the change in y if we make a small change in x. And if we make a small change in x, we make a small area change. So we're going to label that area as delta A, small rectangle with height of y, and a large rectangle with a height of y plus delta y. So what we know is that the actual area is in between the small rectangle and the big rectangle. And what we do here is we divide everything by delta x, because it's not 0, it's close to 0. We're making it really small. It's close to 0, but it's not 0. And we get the following equation. That y has to be less than or equal to delta A over delta x and y plus delta y on the other side. Now this delta A over delta x, change in area over change in x, that's an average rate of change. Okay? But if we make this go to 0, we know that from calculus, average rates of change turn into instantaneous rates of change. So with that, if we make it really small, then this average rate of change would change into the derivative. Because average rate of change changing to instant rate of change would be the derivative. And if we made it go to 0, then the change in y also would get so small. So what we're doing with this rectangle is we're imagining shrinking this x down to nothing. As we shrink that x down to nothing, this change in y shrinks down to nothing as well. And you get a nice squeeze theorem idea where y and y are on both sides, and the middle is the derivative. So because of that squeeze theorem, you would know that y has to equal dA dx. Now if you integrate both sides, if you find the antiderivative of both sides, well, the antiderivative of a derivative would just become a. And on the other side, I now have a proof that the area is the integral. So we're going to find out that this equation gives you your area from the origin up to a value. And if you want to find the area in between two values, you would just need to subtract area of B minus area of A. So we write this, and we've seen this already in some of the examples. I was alluding to it. We've got the integral sign. We put a value on the top and the bottom saying, I'm going from A to B. I want to find the area from A to B. And I can integrate that all the way through. I can think of it as all of those little tiny rectangles added up, which is our limit as, split them up into as n goes to infinity, or as the change in x, right, gets smaller and smaller and smaller and smaller. So two different ways we've looked at this. Sometimes we've talked about the limit on the bottom as n going to infinity, and n being how many times you cut up the rectangles. Every time you cut up the rectangles, you get a tinier, smaller change in x. So in this notation, we're just saying that the change in x is getting smaller and smaller and going to 0, which means you're going to have an infinite amount of rectangles. And then each one of those rectangles has a base and a height. Fu is the height. Xi is the base. And if you added up all of those rectangles, you would get the total area. Notation-wise for integrals, you will always have d something in an integral. And the d something is telling you which variable you're working with. Are you integrating with respect to x? If it was an equation with t's, you'd have dt, because you're integrating with respect to t. So that's a notation thing, just telling you which variable you're using. So notice here, I have a y, but I still say dx because my y equation had to have x's in it. And in order to integrate, I would have to say, if y was x squared, I'd replace the y with x squared before I could use my integration rules. So again, to approximate a definite integral, using the Riemann sums, we can add up all those rectangles, and we pick either the left Riemann sum, right Riemann sum, or the midpoint. So this is a bit of review, just bringing it all together with Riemann sums. So how do we know we need to use a Riemann sum? Well, usually the question will say approximate, because it's not going to be the actual area. Because they don't want to check all three of them, they'll probably tell you to use either the left Riemann sum, the right Riemann sum, or the midpoint. So in this case, we want to use the left Riemann sums, so we're going to need to make 4 rectangles using the left points and having equal intervals. So, careful here. We're going from 2 to 10, that's 8 units, 4 equal sections would be 2 each. So here are our 4 intervals. We're going to go from 2 to 4, 4 to 6, 6 to 8, and 8 to 10. And since we're doing the left ones, this will be our U1, our U2, our U3, and our U4. So the definite integral from 2 to 10 of x minus 2 squared is approximately, so these are approximate signs, the summation from 1 to n of fui, change in x. And we're going to be going from 1 to 4, because we have 4 intervals. And since each rectangle has the change in x, you can factor that change of x out. And just add up all the left-hand sides. Makes your math a little bit easier. Is it a little small? How about that? A little bit better. I do that. And of course, add them up, we get 112. This is a picture of what was happening. Those are the 4 rectangles that we used to get the area. And then when you look at the graph, definitely an underestimate. This one, midpoints would have been way better estimate, it looks like. So in part B it says, do the same thing with the right-hand side, so everything is the same except your U1, U2, U3, U4 are the right-hand points. All of your notation would be the same. What did we get for the first one? 112? You might want to write a note that since we figured out the left and we figured out the right, we could figure out the average of those and get the trapezoidal subs, which would be the best estimate. Obviously, our estimates are not good if one estimate's 112 and the other one's 240. Those aren't very close to each other. All right, unpause the video. Here we go. So, here's our definite integrals, and we've already learned if we did the limit as n goes to infinity or as the change of xi goes to 0, those things will be the same. Our change in x is always the distance from b to a divided by n in different parts, and yet f of ui will always be f of a plus the change in x times I. Okay? So I'm going to draw a little diagram because I think right now if you see this, you might be like, I don't know what just happened there. This a plus change of x, ai. So what we're going to imagine is we're going from a to b. And we have a bunch of sections that are very small, but for the purpose of understanding, we're not going to make them very small. We're going to make them somewhat small. And then here, you have the ith one. Does it make sense what they're saying here with this point right here, that this point is a plus the change of x times I? Because if you had the second one, you'd have a plus 2 changes of x. If you had the third one, you'd have a plus 3 changes of x. So when we get to the ith one, we have a whatever our first value was, plus I changes of x. So now that you see it in the picture, maybe that makes a little bit more sense. When we just write things out with variables, often it can be a little confusing. Especially confusing when you're dealing with infinity and abstractness. So, now we want to take the limit as n goes to infinity of the sum of all of our rectangles. So, f of ai, a plus change in x times I, that is going to be your height. And here, color coding things, notice that we're not writing the change of x anymore. Now we're writing, because of this. We just did a little change there. In yellow, we decided to, instead of writing change of x, we put in b minus a divided by n. And we did the same thing here, because the width of every rectangle change of x is that b minus a to the n. That's the width of all of our rectangles. So now we're going to practice taking the indefinite integrals and changing them to summation form, okay? Which is going to be tedious and a little complicated, and we are in a week, maybe even less, going to learn a shortcut to do this very quickly. Okay? But again, the idea is we're developing the shortcut, so we have to do it the long way first. So we're going from -3 to 3.
Sorry guys, crap. Like crap.
And so the distance between -3 and 3 is 6. So your change in x will be 6 over n. Each height will start at -3 and then have your change in x, 6 over n, times I. This will be your x value that you're plugging in for your height. So as a summation, we want to find the limit as n goes to infinity of the sum of all those rectangles, and we have this as our height. So notice I'm plugging in the -3 plus 6 over n to the I into x squared. So it's getting squared. And this is your width. If you wanted to evaluate this limit, you would have to work at simplifying this so you got one of those formulas that I know that you've been diligently trying to memorize. The summation of 1 to n of I, summation of 1 to n of I squared, and the summation of 1 to n of I cubed. I like how you all look at each other with a guilty look. Have you started that yet? No, I haven't. Okay. So second one. Again, the distance from 2 to 5 is 3, so your change in x is 3 over n. Starting at 2, you do your change of x times I amount of times. That's your x value that you're plugging in. So as a sum, this is the limit as n goes to infinity. And we take that x value and plug it into the equation. So notice here, my equation is 1 over x. So I'm plugging that x value in, and I get 1 over 2 plus 3i over n. This second one, if we actually tried to evaluate that limit, would be quite complicated to do as far as getting the formulas, because the answer to this is the natural log of 5 minus the natural log of 2. Do you see any natural logs written in that sum? No. So that would be tricky to see and connect that. Okay? However, what is the antiderivative of 1 over x? It's the natural log of x. So if we were working backwards from 1 over x, we would get the natural log of x. That is something which on your first take-home quiz, you're going to see a lot of antiderivative stuff. That is something that I would recommend every morning at breakfast, the page that you have of all your antiderivatives, to start working on memorizing those, because it's different to know the derivative of natural log of x is 1 over x. It's different to be able to think directly. If I have 1 over x, my antiderivative is natural log of x. Okay? You need to be able to recognize working both ways. And that takes some practice, especially with your inverse trig ones. Right? Do you still remember what the derivative of cos-inverse of x is? No. So it'd be very hard to recognize that when you had the antiderivative, that you could work backwards. So we've got some work to do on those. All right. We'll do one more together. So the distance from 0 to 7 is 7, so your change in x is 7 over n. Your ui would be starting at 0 and have to add 7 over n I times. Then we plug that in. Extend this. And then I'll get you to try the last one on your own. All right, see, you can check how you did on that one. Oops, maybe not, check. And then try the multiple choice on the next page. See if you can put it together. And that's how the AP exam would ask this question. Does it bother you that they changed the K and I? Were you able to handle more letters in the English alphabet? No, I know. Well, they could have made it W goes to infinity and had a W on top. So again, you'd have to think, if you're solving this, it's good to think of it through this way, right? What's your change in x? What's your UK value? 3 plus change in x times k instead of I, and then write the equation, because sometimes they simplify things, and you can't just pick out the right answer because they've simplified it, okay? First of all, you should have been able to see that it should be B or D because of that 2 over n for your change in x. And then here we have the 3 plus 2 over n times k. They just put the k on the top to match it up, so it is D. Now, can you go the other way? Here's the limit. can we write it as a definite integral?
Oh, yeah. I have a question.
Yeah.
When did they update the question app with the new?
Oh, I haven't downloaded it yet. I'm not sure when the updates go on. What did they have
Okay.
announcements from 3 days ago on there?
Or yesterday.
Yes.
I'm trying to look for the lunch menu. Does anyone in here know it?
It's funny because they talked about when we were as a staff discussing what do you think the app will be used the most for? And we thought the lunch menu, but definitely everybody's going to be checking
I'm so hungry.
what's for lunch. I wonder if they won't update it, because announcements are period 3, right? So it'd be like, give it away if you knew the announcements before somebody else did, because you had the app. That would be unfair. So maybe they don't.
Unfair. Or we just don't have to watch them anymore. I don't like how it's supposed to be.
Okay. Some things to notice. Do you notice that there's no number plus in here? So that makes our lower limit, our a value, 0. In here, if you had 3 plus pi over nk, then you would know your lower value was 3. Next, once we've got that lower limit of 0, your change in x is your distance from 0, your a value to your b value, and since that distance from a to b is pi and our lower value is 0, we would know that our upper value has to be pi. Question? So, it's not sort of a, so, and there should have been more space there, b equals pi. Son of a pi. Yeah, thank you. What is the essence? Because we're supposed to have a space. So now we can write this, that it's going from 0 to pi, the function has to be cos, and you're plugging in x dx. Question. Can anybody graphically do the mental math for this and tell me either what adding all this up to infinity of these rectangles, or what the accumulation of change or area under the curve would be from 0 to pi of cos x? Think. Mathematically, don't add up all those rectangles. There's an infinite amount, and that's difficult math. Okay? But graphically, would you agree this is your cos graph from 0 to pi? And the area under the curve would be this part here, and this part here. Based on what you know of a cos graph, could you see that the green area and the red area are the same? And we know that area above the curve is positive, and the area below the curve is negative. The answer to this is 0. Based on that idea. So we can find the answer even though we don't know the math yet. From the graph, we can say that that answer is going to be 0. So we got all these connecting ideas: area under a curve, accumulation of change, integrals, and infinite sums. And we're going to highly recommend not actually doing the infinite sums, because the integrals are going to be easier once we learn the shortcut. So what do we have to be able to pull from the summation? We have to pull the bottom value. And you see the bottom A value is going to be your negative 3. Then, you can get your upper value, because if 5 is divided by n, you would have to go up to 8. Oh, sorry, negative 3, not negative 3 up 5. I kind of spaced that so you don't. So, b up 5 from negative 3 is going to be 2. Is that enough spaces for you? That's good. Okay. I just have to think my lower limit's negative 3, and my total change is 5. I just have to go up 5 from negative 3 to get b is negative 2. And this part inside is my x, so I'm going to have the integral of the cube root of x. Try the last one here on your own. I'll put up the answer. Right? So, holistically, you have to see that this is your x, and you have 1 over x squared. In that x, you get your lower limit by the 6. So I get my lower limit from the 6. And I know my distance from b to a, or b minus a, has to be 9. So if I am starting at 6, I have to go up to 15. I think you could probably write that 15 down without showing much more work. You could probably do that mental math. So now I've got, it's going from 6 to 15. I look at this part, and I would say I've got 1 over green box squared, so that's 1 over x squared dx. So the next question is very similar, except it says write 3 different ways. So we're going to go, right, I could use a is 4, go from 4 to 10. This would be the most simplest way to go about this. And this is what I would think you would all come up with first. Lower value is 4. Your change between your lower and upper has to be 6. So we have to go from 4 to 10. And we've got an x squared. Couple of ways you can do a second way. You can choose a new starting point. So we had a equals 4, but you could get the same one if you chose a different starting point. Why you would want to do this, I'm not sure, but preparing us for multiple choice questions where they don't give you the regular one. Like I would say every time I would find this first. Because that's your regular one, that's the easy one. But it doesn't match up with your multiple choice. They have different answers. So how could we write it in different ways? Okay? So if the multiple choice had a 0 at the bottom, that would mean your a value is 0. And a 6 at the top would mean your b value is 6. That would still give you your 6 over n. That makes sense. That's perfectly fine. But now, you would need to have your UK equal 6k over n. Does that match up for this question? How does this work? No, but it would work if we had an extra 4 in front, and then you replaced your k, x with 6k over n. An easier or another way of seeing this whole thing is to go back to grade 12 and think about transformations. If I replace this x with x plus 4, how does that move your graph? That would take my x squared graph and move it 4 units to the left. Agreed? Now, if the area under the curve from 4 to 10 is what you're looking at, and you move everything 4 units to the left, can you see that you would now be looking from 0 to 6? That area would be the same. So we can use transformations as well to think about which ones are equivalent. Okay? So this method was thinking about a new starting point, a new ending point, and then what would your UK be? It'd be 6k over n. That replaces the x, that just replaces this part, and it still matches up. Or we can think about transformations. So here's a third one. I don't know if I'd recommend this one, but we have a 6 out in front. So we put a 6 out in front there. You have your a value as 0. So your x value, and you put your a value as 0, and your b value as 1. Having that 6 out in front of your integral is the same as having the 6 inside of your integral. Again, I would recommend doing the first one, and then we would have to think about horizontal, vertical changes, and things like that. Okay. What do we got? 3 more questions? 4 more questions? 5? Oh, we got more. Maybe we won't finish. We're not going to finish. We'll have to leave a little bit for tomorrow. So try this one on your own. We'll end with this one. If you get 1, see if you can find another one. That would definitely be the easiest one to find. Here's an example of another possibility. With transformations, you can see that that's just shifted to